This is Group Zero's EXPO introduction video. Our project is on the waterless automated solar panel cleaner. In today's presentation, we will be briefly going over some background information. We will then explain the importance of cleaning and how our electrode subsystem works. Then we will be talking about our design specs and impact of SolarStar 1 and 2. Lastly, we will demonstrate the CAD model of the proposed WASPC design and showcase the efficiency power output projections. Which is why our goal is to design an automated and waterless cleaning apparatus to address this problem. Solar energy growth is one of the most dominant sectors of the renewable energy market. 46% of new electric capacity came from solar energy, which is why solving this problem is so significant. These solar panels are usually constructed in sunny, open environments where panels are likely to be exposed to a large amount of dust that can cause the panel surface to be shaded from the efficient use. By using traditional cleaning methods, the cost of the entire process could range anywhere between 15 to 35 US dollar per panel per year. And since SolarStar, a solar farm in Arizona, hosts about 1.7 million solar panels, the cost adds up to 25.5 to 59.5 million a year. We want to minimize the losses by reducing the impact of dust particles using our cleaning system.
Moving on to why cleaning is important. The graph shown on the top right is a MIT research team data for relating power output versus dust coverage. Under that plot is the percentage change of power output versus dust coverage, which correlates closely to the MIT research team's data. It can be seen for merely 5 milligram per centimeter squared dust coverage results in a 50% loss in power output. Now, this is substantial, mainly because if you put it into dollars perspective, every gigawatt hour lost is equivalent to $166,000 of revenue loss. Now, for the highlight of the WASP-C cleaning system is the electrode subsystem, which consists mainly of a charged electrode and an oppositely charged solar panel surface. The solar panel surface will be coated with aluminum zinc oxide. More about that in the next slide. The main way that this magnetic force will work is to counteract the adhesion forces and the gravity forces. The result of these forces can be shown in this slide. The pictures below also show how the electrode will work. The dust particles are shown to repel from each other and then be attracted to the electrode. So now the conductive film, which is the aluminum zinc oxide, will be applied to the solar panel surface using a atomic layer deposition method, which mainly is purging the outer atoms of the glass that is laid on top of the solar panel, and then replacing these atoms with a very thin layer of aluminum zinc oxide. The figure on the top right shows a depiction or an example of that. On the bottom right of the slide is another image showing how the dust particles will be charged and how they will be repelled from each other and from the surface of the solar panel, then attracted to the oppositely charged electrode above.
SolarStar 1 and 2 will be the main focus of our design constraints. SolarStar is a grid-scale solar farm located just outside of Los Angeles and has 13 square kilometers of solar panels. It produces an average of 1,655 gigawatt hours of energy, which is enough for 250,000 households. The solar farm features the SunPower 128 cell panel, which we will be used to model our cleaning apparatus. The ideal conditions for the electrode subsystem is to have 20 to 30% humidity, which is met at SolarStar. This is our proposed design for the waterless automated solar panel cleaning system. Our apparatus is designed for ground-mounted solar panels, as you can see in the images. Our apparatus features a microfiber brush, an electrode, and an air manifold. The translational motion of our cleaning apparatus will be facilitated by timing belts and pulleys, as well as a linear guide rail system. The motors are attached to the top and bottom of the solar panel frame, and as they rotate, the cleaning apparatus can slide along the surface of the solar panels. The first stage of the cleaning will be conducted by our air manifold. A single blower fan is used to push air out of a thin slit at the front of the air manifold, which will push off any large debris on the surface of the solar panels. The next stage is the electrostatic repulsion, which will be done by an electrode. A thin film of aluminum zinc oxide will charge the dust particles on the surface of the solar panel, and these dust particles will get attracted to the oppositely charged electrode that is located above. The last step in the cleaning process is our microfiber brush, which will be used to remove any remaining debris from the system.
Installation of the waterless automated cleaner at a farm such as SolarStar should result in an increase in annual electric power generation. In order to quantify this benefit, a model involving 4 scenarios was analyzed. Those include no dust, annual cleaning, biannual cleaning, and automated cleaning. A model of dust accumulation rate over 1 year was used to calculate the efficiencies of these 4 scenarios over 1 year. These efficiencies were then used to calculate the expected annual power outputs of each of the 4 scenarios to compare them to the actual yearly output of SolarStar. Our model and calculations have concluded that automated cleaning does indeed result in higher power outputs for solar farms than any other real-world method. We have also concluded that operational cost of the apparatus is essentially negligible to the expected benefits of its installation. Thank you for your time and see you at EXPO.